The rules of the game have changed. It's not good enough to be concerned with making a good quality part. Now we have to be concerned about what is the life of that part. How long is this part going to remain a good quality part? And those are some of the concerns that we have here in the HALT lab. With the information that comes from this HALT lab, the design engineer will be armed with the information to have that perspective. What will the quality, what will the reliability of the product be 9, 10 years from the manufacture date?
Our major claim of fame will be that we can isolate intermittent problems quite rapidly. We don't take 6 months to do it. We can do it within a week's time.
One good diagnostic report could pay back the value of the 3x3 HALT chamber at least 10 times, if not more. The concept of highly accelerated life testing in the design process is to identify the robustness of the product.
HALT enables you to find the weak link in the chain rapidly. You can find the portion of your product which is most likely to break, and with a very quick design revision, make a change, and through successive HALT testing and design revisions, rapidly identify all the potential failure modes of your product before you put it into the field.
These are industrialized heavy-duty chambers that are capable, in this lab at least, capable of establishing temperature cycling and vibration stress. And recently we put in salt spray, and we're also capable of establishing humidity, 100% humidity. All of these various stresses can be imparted individually or all together depending on what we're looking for in a given product.
These chambers are capable of achieving 200 degrees C and 150 degrees minus C. And we can do that at a rate of 72 degrees C per minute because of the fact that we use liquid nitrogen to cool the chamber. It's a very quick ramp rate on our temperature. Above the three lights is the what we call the plenum. That's where the temperatures are generated by the use of LN2, liquid nitrogen, and 3 banks of coils that can heat up the chamber to plus 200 degrees C. The air is then forced down through the ductwork onto the part. Under the table we have 9 pneumatic hammers. Each one vibrates randomly, which causes the vibration to travel through the table, through the fixture, and eventually into the part under test, causing vibration across all 3 axes in what we call 6 degrees of freedom. The tabletop itself has a titanium sheet on it which protects the hammers from the extreme temperature variations. Thereby we are able to vibrate down through the cold cycle and all the way through hot. The doors on the chamber are 6 inches thick of insulation with stainless steel linings. Each door is equipped with 6 plate glass windows of tempered glass, and at minus 150, which is a temperature that we have attained in the chamber, it's very well insulated from the outside. The insulation in the doors also acts as a good sound barrier when we're vibrating at, say, 75 Gs inside the chamber. It's relatively quiet outside. The thing that impresses me most about the chambers is the fact that we can vibrate through the temperature cycle, and we are unique in that fact.
It's unique to apply both vibration and thermal stresses at the same time. And we're really pushing the envelope because now we're applying humidity and salt spray, and we've not had the pleasure of knowing how our product's going to react in those simultaneous stresses.
So all of the stresses we do in the lab have to be normalized with the same stresses that come from the field, be they temperature or dynamic loading, vibration, or whatever, salt, humidity, and that sort of thing. We have to feel comfortable that all those stresses are the same.
We instrument the part in the field the same as we would in the chamber, so now we've got a direct correlation. From this we can project the life expectancy of the part. Is there inherent flaws in the design? If there is, we'll find them. This is our GHI portable analyzer. With this analyzer, we correlate field data with lab data. It works very well in both environments. What you'll be seeing is raw data from the field. This is from a 94 Mustang on an electronics module. From this, we can break this up into peak distribution calculations or a spectral analysis. This one shows an inherent resonance about 37 hertz. This module may have to be re-engineered because this is a very destructive frequency for it to resonate at.
The idea of test to failure is a very important one here, and we're very careful to make sure that the test to failure is a test to failure within the dynamic range of the part. That's why we start with the limits of the part. We identify the strengths of the part, and therefore we work with programs of stress programs that are within that dynamic range that we establish with the part, so that now we can stress parts and monitor the time to failure, and we know that we didn't cause that part to fail. The part fell because of normal fatigue physics of the design. In highly accelerated testing here in the lab, we do it in two ways: predictive accelerated testing and diagnostic accelerated testing. The predictive is where we actually take new designs and actually chart with sampling, establish the fatigue time curve of the unit, and eventually predict the reliability of this unit in the field. The other end of it, the diagnostic, is a situation where parts already in the field might begin to build up a problem for some reason. We would go backwards, actually going from the field measurements. In the lab, we try to replicate those failures, and we carefully monitor the stresses that are required for us to replicate the exact same problem, and that gives the engineer much more information as to why his part is failing in the field, and eventually eliminating the problem with redesign or whatever it takes to make that problem go away.
We had a problem occurring on the starter solenoid. About 2 years in service, the solenoids within the starter would short out within the coil, and we weren't sure exactly why this was occurring. We had been trying to reproduce this failure mode for about 2 months using standard electrodynamic shakers. We had had some initial success, but we really weren't able to reproduce it repeatably. What we found about the HALT chamber is that it had three-dimensional capability, and that's really what drew our interest in the HALT process. So we weren't really sure how well it would work. We weren't familiar with it, and so we gave them some parts to try out. Within about a week, we had reproduced the failure, and so we set up a controlled test to compare the old and the new wire.
I think the greatest rewards I've seen using the HALT method has been a time when I was working on the Ford Mondeo in Europe. We had a situation where we needed to do, again, an A to B comparison. I flew over to America from Germany, Cologne, Germany, and spent a week here. And we were able to determine that the changes were acceptable and totally evaluate the module using the HALT method in just a week. Again, normally that would take 4 weeks.
The goal in any kind of testing is to be able to reproduce your field failures in a controlled, accelerated environment, and that's really what we've done.